Okay. Can you see?
Oh, yeah.
Yep. Okay. So we're finished with lines in 3-space, and we're moving on to planes in 3-space for the rest of the week, and that's the last topic in the whole course. So we got there. We're going to start off today with the vector equation of a plane with me this morning, and then the recorded video will be on the scalar equation of a plane, which is much more useful, but we will learn both. So our learning goals for this morning are learning to write the vector and parametric equation of a plane in 3-space. And I showed you this kind of picture at the side. It's supposed to be 3-dimensional, where the XY plane would be like flat on your table, and it's made by the x-axis and the y-axis, okay? And then the YZ plane is up and down, so to the right and up. And the XZ plane would be forwards facing you and up. And those are just pieces of it, but it gives you a good idea of what the 3 coordinate planes, we'll call them, are: the XY plane, the XZ plane, and the YZ plane. So our second learning goal is, given a point in 3-space, we can determine whether or not it lies in a plane, which will be much easier once you learn the scalar equation of a plane this afternoon. And also understanding what the coordinate planes are. We've kind of gone over what they are there, formed by the different axes. So this all tells you about the vector equation of a plane, but I have a video that has this picture and explains it really well. So I'm just going to show part of that video as an introduction, and then we'll go from there. I think it might be better if I turn that light off. All right.
In this video, we'll take a look at the equation of a plane, and actually 3 different kinds of equations. So first of all, this yellow thing is supposed to represent a plane. It's actually, this isn't the entire plane. It does extend in all those directions infinitely, so this just really represents part of a plane. Now, we're going to talk about vector and parametric equations first. So let's say that we have this arbitrary point in the plane. I'm going to call it the point x, y, z. So x, y, and z could be any point whatsoever. Now, one way to define that we're talking about this specific plane is if we have a particular point in the plane, like -3, 4, 5 is a point, and 2 vectors that are in the plane or parallel to the plane. Those actually mean the same thing, like the vectors u and v here. Now, this arbitrary point is in the plane if the vector that goes from -3, 4, 5, where the tail of this vector is, to that vector x, y, z, if that vector is also parallel to the plane. Now, we would know that that vector AP is parallel to the plane if we can write that green AP vector as some linear combination of the vectors u and v. So, for example, the way it's drawn here right now, it looks like that AP vector is 3 vector v's plus a vector u, and that's the parallelogram law, or you could look at half of it, it's a triangle law. And so AP is in the plane, okay, if you can write that vector as some linear combination of the 2 vectors that are in the plane or parallel to the plane. Now, let's draw a vector that goes from the origin up to A and also from the 0, 0, 0 point up to point P. And so we're looking at this triangle here right now. Now, the vector that goes from O to P, which is OP, is equal to OA, this one here, OA, plus the green vector, which we would call AP. So that's just a triangle law, OP equals OA plus AP. Now, as I was talking about when those u and v vectors were here, the vector AP is in the plane if you can write it as some linear combination of the vectors u and v. So s and t here are scalars. So that's what I mean by it's some amount of vector u's plus some amount of vector v's. The way we drew it, I had 3 vector v's and 1 vector u. So s and t are just scalars, or parameters. And so that's just writing that AP vector as some number of vector u's plus some number of vector v's. Now, I'm going to substitute in place of the AP SU plus TV. And so this is in general what a vector equation, the structure of it looks like. And so this is how we would write our vector equation. This is just the structure. This is what it would look like. Now, OP is a vector that goes from the origin to this arbitrary point x, y, z. So this OP vector would be the vector x, y, z. Remember, when you find the vector between 2 points, you subtract the coordinates. So O, or the origin here is 0, 0, 0. When you go x minus 0, y minus 0, z minus 0, then we would call that the vector x, y, z. OA is a vector negative 3, 4, 5, because it goes from the origin to the point negative 3, 4, 5. So that's OA. And then SU plus TV. So S times vector U, which is a 6, negative 5, 1 vector, plus T times vector V, which is a negative 1, 3, 2 vector. So that's what a vector equation looks like. It looks a lot like the vector equation of a line, except you have another parameter here, because a line is only a one-dimensional thing, whereas a plane is two-dimensional. So you need two vectors in the plane as opposed to one vector just parallel to a line. So that's what a vector equation looks like.
Okay. Did you catch on to that? Okay. Yeah, you can hear it. Okay. What do you think vectors U and V, what would I call them? They were direction vectors of the plane. Okay, so instead of having vector U, I might call this vector U vector M1. So that's my first direction vector of the plane. And instead of calling vector V, vector V, oh, I don't have a blue pen here. I might call it this one vector M2. Okay, so U and V are really just two direction vectors for the plane. So whereas a line only needs one direction vector, a plane needs two direction vectors to define it. So we have our vector equation is really going to be R, which represents X, Y, Z, same thing. R is going to be the vector of a known point on the plane, okay, which is little a, or we can say a point-to-point vector O to A like he used. But that represents a known point on the plane. Plus we're going to use two parameters. So I'm going to use U as one of them because S is kind of looks like a 2 often, plus T times our other direction vector. So that's the structure of the vector equation of a plane. And I've kind of given that description up there, kind of how the same way that he developed it. And M1 and M2 are two non-collinear direction vectors that are in the plane. Okay. All right, so a plane can be completely defined by given a point and two non-collinear direction vectors. So that's this setup here where you're given this point right there, and then you're given the two non-collinear direction vectors. So that's the easiest way to define a plane if you're given a point and two direction vectors. But you can also find the equation of a plane if you're given three non-collinear points. So given any 3 points that don't line up in a line is what non-collinear means. We know that we can make two vectors out of those 3 points. One vector there, which could be one of our direction vectors, and one vector here, which could be one of our direction vectors. And then we'd have two directions, and then we have 3 different points to choose from for our point. So we're going to start off with some examples then. Find vector and parametric equations of the plane containing these 3 points, A, B, and C. So I always like to do like a little diagram somewhere here of a portion of the plane. Usually people use parallelograms to draw a portion of a plane, rectangle, whatever you like. And I'm just going to draw my 3 points randomly. A, B, and C. And then I'm going to actually write what their coordinates are beside them. So we know that we can make two direction vectors from these 3 points that all lie in this plane. So there's one of my direction vectors. That's going to be AB. And another one of my direction vectors is going to be AC. So I'm going to find vector AB, which is B minus A. So that's going to be 2 minus 1 is 1, -3, 4. And that doesn't have a smaller, nicer scalar multiple because all we're concerned about really, this is going to be a direction vector. So I'm just going to let this one be M1. And then I'm going to find vector AC. So C minus A, that's going to be 2, 5, 0, because -3 minus -3 is 0. And that's going to be my M2. So my vector equation is going to be R equals, and then choose one of my points. And remember that it's really representing the vector from 0, 0, 0 to that point that gets you to the plane. Okay, so I'm going to choose point A. So 1, 0, -3 plus U times my first direction vector plus T times my second direction vector. It doesn't matter what letters you use for parameters. Common ones are T, S, T, U, V, P, Q, I would say, are the most common ones people use for parameters. And parametrics, just like they did with lines, fall right out of the vector equation. So we can say that the x parametric is x is 1 plus 1u, which is just u, plus 2t. Y is 0, which we don't need to show, minus 3u, plus 0t, so we don't need to show that either. Or sorry, plus 5t, my bad. And z is going to be -3 plus 4u plus 0t, which I don't need to show. So those would be my 3 parametric equations. Any questions for that one? Okay. Our second one, find vector and parametric equations of the plane containing the parallel lines. So I'm going to do a little picture again. So if I have parallel lines, it should mean they have the same direction vector. So if I look at the 2 lines that are given here, there's the direction vector of the first line, and there's the direction vector of the second line. And we can see that they're parallel because they're scalar multiples of each other. So really they're both the same direction. So I can only use one of them as one of my direction vectors. So far I know that I have one of my direction vectors for my plane is going to be 3, -1, 1. Does anyone have an idea how I can use these equations of the lines to get a second direction for my plane?
Use a perpendicular line.
Okay, a perpendicular line is going to be like this, right? Or do you mean like this?
Like that.
And how would I find that?
Find n.
Okay, so a line doesn't have a line in 3 space doesn't have a normal, only a plane does. And we haven't defined that plane yet because we need another direction in order to do that. Because remember, a line in 3 space has an infinite number of normals. So I can't just find a normal by looking at this direction. So there's got to be another way to get another direction. Any other ideas how to get another direction from the equations of these two lines?
Like, kind of like the perpendicular line, you could do a line between the 2 points.
Right. So good. So we know a point on this line for sure. I'm going to call that point Q1, Q subscript 1. So we know a point on this line here is 2, 4, 1. And we know a point on this line, which I'll call Q2, is 1, 4, 4. And if I make a vector from Q1 to Q2, that's going to give me a second direction vector, a second vector that's in the plane that's different from M1, hopefully. Okay? Well, it is because these are parallel, not the same line. All right, so then we're going to find Q1, Q2 vector by subtracting. So 1 minus 2 is -1. 4 minus 4 is 0. 4 minus 1 is 3. And so my M2 then is going to be -1, 0, 3, or I could have chosen 1, 0, -3. It's up to you. So now I have two different directions that aren't scalar multiples of each other, and that's what I need. And I also have 2 points to choose from for my point. So my vector equation is going to be R equals, so the vector from 0, 0, 0 to 2, 4, 1 is 2, 4, 1 plus U times -1, 0, 3 plus T times 3, -1, 1. These obviously could be in either order. I think I probably did an order. You probably would have put the 3, -1, 1 here, but it doesn't matter. So that's the vector equation of the plane. Remember, it's got 2 parameters instead of 1, and that's how you could, even though a line and a plane both start with R, you can tell whether we're talking about a line because it would only have 1 parameter, and a plane would have 2 parameters and 2 direction vectors. And then the parametrics would be x equals 2 minus u plus 3t, y equals 4 plus 0u, so I don't need to show that, minus t, and z equals 1 plus 3u plus t. So then we've got vector and parametric equations of the plane containing parallel lines. Okay, find vector and parametric equations of the plane containing these intersecting lines. So here's my plane. Here's one of my lines, R1. Here's my other line, R2, and they lie within the plane. So these are intersecting lines, meaning they have different direction vectors. So this is my M1, and this is my M2. They're not scalar multiples of each other, so that's pretty easy. I've got 2 directions there right away. And then I could choose either point, because both of them lie on the plane. So there isn't any really extra work I have to do here to write the vector equation of the plane. I'm going to choose a point. I'm going to choose 6, 5, -2. Plus u times my first direction vector, 4, -2, 1, plus t times my second direction vector, -1, 5, and 2. And it wants parametric equations as well. So they're going to be x equals 6 plus 4u minus t. y equals 5 minus 2u plus 5t, and z equals negative 2 plus u plus 2t. So intersecting lines, the information is really easy to pick out. The fourth question, determine vector and parametric equations of the plane containing a point. So here's my point Q, 8, 3, 5, and a line R. So we want vector and parametric equations of the plane containing that point and that line. So I know I've got one direction right here. That can be my M1 is the direction vector of the line. Any ideas how I could get a second direction?
Go from the point negative 3, 4, 6 to Q.
Perfect. Okay, so go from the point negative 3, 4, 6 to Q here. So I could call that point anything. I'll call it A, negative 3, 4, 6. So if I make the direction AQ, that's going to be another different direction. So let's make that vector AQ. So I'm going to do Q minus A. 8 minus negative 3 is 11. 3 minus 4 is negative 1. And 5 minus 6 is negative 1. So that's going to be my M2. So now I have my two different directions. So my vector equation, I'll just choose the point 8, 3, 5. Plus u times negative 5, negative 2, 3, plus t times 11, negative 1, negative 1. And the parametrics. X would be 8 minus 5u plus 11t. Y would be 3 minus 2u minus t. And z would be 5 plus 3u minus t. Excellent. So you always have to get two directions and a point in order to make your vector equation. You have to make sure your two directions are not scalar multiples of each other. All right, so we've gone through a bunch of different pieces of information they could give you. So we did 3 points, 2 parallel lines, 2 intersecting lines, and a point in the line. All right. Does the point 4, 5, negative 3 lie in this plane? Any ideas?
Maybe you could use parametrics.
Yes. Okay, so that is what I would do first. I'm going to use parametrics here. So x equals 4 plus 3p minus 6q. Y equals 1 minus 2p plus 6q. And z equals 6 plus p minus q. And I'm going to replace x, y, and z with 4, 5, and negative 3. So here's kind of my step 1, is just writing out the parametrics. So step 2, I'm going to replace x, y, and z with 4, 5, and -3. And it should start to look really familiar to you, similar to what we did yesterday, where we've got 3 equations and 2 unknowns. And I want us to get them to look like yesterday's ones. So I want the P's and Q's to one side. We might as well keep them on the right side, and we'll move the constants so they're on the same side. So all I'm going to do is subtract this 4 over. And subtract 1 over. And subtract 6 over. And I'm going to call these equations 1, 2, and 3. So it's going to be the very, very similar, I won't say exact same thing as what we did yesterday. We're going to solve 2 of them. Lock the other one away. And if the solution of the 2 that we solve works in the left side, right side check for the third one, then the point does lie on the plane. If it doesn't work, then the point does not lie on the plane. And if I'm looking at my 3 equations, I'm seeing that these guys both have 6 Q's in it. So I'm going to lock this one up. And I'm going to solve 1 and 2. And I'm going to eliminate Q. And I don't need to multiply to do that. So this is step 4. Once we have scalar equations of the plane this afternoon, it will be so easy to see whether a point's on a plane or not. It will take like a minute. So in this case, in order to eliminate Q, we're going to add. So we would get 4 equals P. The Q's would cancel, so that's nice and easy. So now we're going to find Q. So I'm going to choose the one with 0 in it, I think. So 0 equals 3P, but P is 4, minus 6Q. Subtract 12 on both sides. Divide both sides by -6. And you get that. Q equals 2. So now we've solved the system. So step 5 is going to be to check. So we're going to check. Check in equation 3. And that's going to let us know whether the point does lie on the plane or it does not lie on the plane. So the equation we locked away, or I chose to lock away, was 3, which had, oops, I made my sides a bit lopsided, oh well. Left side only has -9 on it. Right side has P minus Q. P was 4. Minus 2 is 2, so they don't equal. So we would say, therefore, left side does not equal right side. Therefore, the point 4, 5, -3 is not on the plane. Now, instead of saying the plane, there's a short form for the plane. Because P is used for point of intersection or for a point, and L is used for line, capital L is used for line. We can't use point P for plane as well, so we use pi. So the short form for a plane is pi. If you want to say not on the plane, you could say not on pi, which is kind of cool. And sorry, this would have been step 5 is the checking part. You're keeping track. So that took us 5 steps to get to the answer, whereas once you learn how to find the scalar equation of a plane, it takes 1 step. You just need a left side, right side check.
So I guess eventually the same way they use like point of intersection and line of intersection, they might do plane of intersection or something.
Yes, exactly. So when we get there on Thursday, we'll be looking for pi OIs in some cases, pi of intersection.
Okay.
Will be okay. That's the short form for plane of intersection, which is
Cool.
coming on Thursday. Thursday's lesson is going to be good. It's going to be fairly long, and you need scissors and tape. There's diagrams to go with it. And then there's practice, but there's no assignment Thursday. And then Friday, we're just going to do a few more examples of the same stuff we did Thursday. And then there's the last assignment of the year. We're getting there, guys. You're doing awesome. Okay, question 6. Determine vector and parametric equations of the XZ plane. I'm just going to go back to our first little picture here from the front. So this is the XZ plane here in orange. If you look at your first, remember it extends in both directions, but to get the equation of a plane, you need a point you know is on it and 2 directions. Does anyone think they know 2 easy direction vectors to find for the XZ plane? Okay, I'll help you out. The x-axis is one direction that you could use. And the z-axis would be another direction that defines the XZ plane. They're not collinear, and they're easy directions. So we could have our M1 direction be in the direction of the x-axis, and we can just choose any number in 0, 0. 1's usually the one people choose because it's easiest. So the direction 1, 0, 0 is the direction of the x-axis. And the direction of the z-axis, easiest way to write it would be 0, 0, 1. So there's my 2 direction vectors. How about getting a point on this XZ plane? What would a point that's on this plane look like?
You could have 0, 0, 0.
You could for sure have 0, 0, 0. So we could choose the origin as our point. What about a point like here? See where I put my pencil mark? It's not on the origin here. What would a point like this be constructed like?
Would it have to have the y value be 0?
Yes! Bing, bing, bing. So you could choose any point here, right? As long as you have a number, 0, and then another number, then it's going to be on the XZ plane. So this is any point on the XZ plane would be constructed like this. Awesome. So I would honestly, most people would choose that one because it's the easiest one to choose. You know it's on it. It's really straightforward. But any point constructed like this would also be on the XZ plane. And we need vector and parametric. So my vector equation, I'll choose 0, 0, 0 because it's easy, plus u times 1, 0, 0, plus t times 0, 0, 1. And the parametrics are going to look super easy. So my x parametric is just going to be 0 plus u plus 0. So x equals u. Y equals 0. And z equals 1. Or sorry, t. 1t. So those are the parametrics of the XZ plane. All right, so our last question here, a plane pi has a vector equation given to us. Determine the point where the plane intersects the z-axis. So they're showing us that point there. They want us to figure out what that point is. And kind of the way we were thinking about it, is there any of these that we know for sure?
Yes, we know that X and Y have to be 0.
Awesome. Okay, so we know that point there is constructed like that because it's right, that point there is right on the z-axis. So it's 0 in the x direction, 0 in the y direction, and then so many, it looks like it's going to be, they're setting us up to get a positive number. We're not sure if we will, but so many up. Okay, so that's how it's going to be constructed. So right away, we know that when the plane intersects the z-axis, x is going to equal y is going to equal 0, which is going to be important for us. So does anyone have an idea of how we could find that point given the vector equation? And the information that x equals y equals 0.
Could we use parametrics?
We could. Okay, so our parametrics are going to be x equals 6 plus u plus 2t, y equals -2 plus 3u plus 2t, and z equals 3 plus u times 0, so we'll leave that out, minus t. And we know that x and y are both 0. So if we solve for u and t in this system, then we will know the u and t that make this true, where x equals y equals 0, and we know that that's going to be where our plane hits the z-axis. So I could just take the u and t and sub them into the z parametric to get the z-intercept. It looks like we only need t. So I'm going to solve this system so this is kind of my first step. Now I want to get the constants on the other side.
Do we always have to move it around, Ms. Northwood, or could we?
No, if you don't mind working with it that way, it's just a personal preference, I would say, for me.
Okay.
This is obviously set up to eliminate t, even though t is the one we really need, but we'll do that. So let's solve 1 and 2, and we're going to eliminate t. By subtraction. So we're going to subtract. So -6 minus 2 is -8. U minus 3u is -2u. And 2t minus 2t is 0. So we get that u is 4. Now we want to find t. I'm going to choose the second one. So 2 is equal to 3 times u, which is 4, plus 2t. Subtract 12 on both sides. And we get t is -5. So then what we would do is we would take our values of u and t and sub them into the z parametric to find the value of z when x and y are 0. which will be our z-intercept. So now we're going to come up here, find z-intercept. So we want to take our z parametric, z equals 3 minus t, and sub in -5 for t. If there was a u, we'd sub that in as well, but there isn't. Z equals 8. So that means therefore the z-intercept is 0, 0, 8. So that plane touch crosses through the z-axis at the point 0, 0, 8.
So if we would have just solved for t right away, like eliminated u, we wouldn't have had to do the rest.
Correct. So if you'd multiplied by 3 in this one, you wouldn't have had to find u at all, because you would have seen ahead, Hannah, that there was no need to find u because we didn't need it to find z.
Okay, thank you.
Yep. Okay, so that is the vector and parametric equations of a plane. The next lesson will be scalar, which is much nicer. It has this form that you're used to. So that's what you're going to do next in the next video lesson. So that's what the scalar equation of a plane looks like, where the normal is A, B, and C. Very, very useful form of a plane. And we'll be working with that going forward Wednesday, Thursday, and Friday. Okay, I'm going to stop recording.